Hello guys, I'm back with another chapter, Electromagnetic Induction. I have been solving previous year Neet questions and I'm uploading it in YouTube. Hope all of you are utilizing it. Now today, we are going to discuss about electromagnetic induction chapter. Let's get started. The very first question is based on magnetic flux. Let me read it out. A circular disk of radius 0.2 meter is placed in uniform magnetic field of induction 1 by pi Weber per meter square in such a way that its axis makes an angle 60 degrees with magnetic field. The magnetic flux linked with it, they're asking. Okay, so we know the formula for magnetic flux. So magnetic flux formula phi is equal to B into A into cos theta, where theta is angle between magnetic field and area vector. Okay, so they gave radius. Then how to find out flux? Flux is equal to B is 1 by pi, area is pi r square, r value is 0.2 square into cos theta, theta is 60 degrees, cos 60 is 1 by 2, pi will get cancelled, 0.2 square is 0.04 into 1 by 2, which is equal to 0.02 Weber. Which option? Option C is correct. So let's move on to the next question. Next question is based on Faraday's law of induction. Okay. A 800 turn coil of effective area 0.05 meter square is perpendicular to magnetic field B equal to 5 into 10 power minus 5 Tesla. Okay. Observe this diagram. Area of the coil is perpendicular to magnetic field. This is the way to represent. Now area of this coil is represented in the direction of magnetic field here like this. This is the first position. Now what is the value of theta 1? Theta 1 is equal to 0 degrees because area vector and magnetic field both are in same direction. Okay. They gave values of magnetic field and area also. Magnetic field is equal to 5 into 10 power minus 5 Tesla. Area is equal to 0.05 meter square and number of turns. We didn't have only one coil. We have different numbers. So many numbers. That is 800 number of coils. Okay. When the plane of the coil is rotated by 90 degrees and any of its coplanar axis is in 0.1 second, the EMF induced, they are asking. Okay. Now theta 2 is equal to 90 degrees. It is rotated to another angle. So we know the formula for induced EMF magnitude, that is delta phi by delta t. So I am just considering only magnitude. Actually formula is minus d phi by dt, right? I am finding only magnitude of induced EMF, which can be replaced as phi 2 minus phi 1 by t2 minus t1. Initial time is 0 and the time they are given in the question is 0.1 second. Then induced EMF is equal to phi 2e can be replaced as BA cos theta 2. Phi 1 is BA cos theta 1 divided by T. BA is common. B value is 5 into 10 power minus 5. And the area I can replace it is as 5 into 10 power minus 2 cos theta 2, or else you can write down it is as cos theta 1 minus cos theta 2. Okay. Theta 2 value is 90 degrees, so cos 90 minus, I'm finding only magnitude, cos 0 divided by time. Time value 0.1 second. Cos 90 is 0. Cos 0 is 1. You are going to get minus 1. So as I am taking it is as magnitude, then it can be replaced as only plus 1. So its final answer is going to be So minus 1, 1 10 power minus 1, it will goes to numerator, 1 by 10, it will be 10 power plus 1, 10 power minus 1, 10 power minus 6. Answer is going to be 25 into 10 power minus 6. Which option matches? Okay, so no option. We didn't consider number of turns. So what is the total number of turns here? It is multiplied with n here. So which is equal to 800 into 800. That is it will 25 into 8 is going to be 200. So it can be replaced as 200, 2 into 10 power plus 4 into 10 power minus 2 minus 6, which is equal to 2 into 10 power minus 2. Answer is 0.02 volt. Which option matches? Option A is the correct answer. Hope you understood. Okay, next question. See, I did consider only magnitude here. General formula is minus d phi by dt. As we are getting minus 1 here, that negative will become positive. Anyhow, I am considering only magnitude here. So you can answer with the help of this also. You will get the same answer. Okay. Let's move on to the next question. Observe question number 3. A uniform magnetic field is restricted within the region of radius smaller. Okay. Observe the diagram. We have two different loops, loop 1 and loop 2. Loop 1 is enclosed by a magnetic field. So loop 2 is outside of that enclosed area. Okay. This magnetic field is linking with only area 1, not with area 2, not with loop 2. That's the meaning over there. Then what is the question they're asking? Then induced EMF. Okay. So induced EMF formula minus d phi by dt, right? Is equal to minus d phi by dt, where phi is equal to phi is equal to b into a, that is minus d by dt ba cos theta. Here area vector and magnetic field both are in same direction. Here cross represent magnetic field is into the board. So area vector also into the board here. ba cos 0. Cos 0 is going to be 1. Area of this coil is pi r square, which is constant, comes outside. Magnetic field is varying with respect to time, and it is replaced as dB by dt. So EMF induced in loop 1, this is in loop 1, is minus pi r square dB by dt. Okay, so let's talk about EMF induced in loop 2. In loop 2, which is equal to minus d phi by dt. Is there any flux linking with loop 2? No, there is no any kind of flux linking with loop 2. That means magnetic field linking with loop itself is 0. So you are going to get answer 0. So observe the option. Which option matches? Option D is the correct answer. With loop 1 alone, magnetic field is linking, not with the loop 2. That's why EMF induced in loop 1 is minus pi r square dB by dt, wherein loop 2 is what it is 0. Sir, in the question they said dB by dt is changing. Why can't it is going to interlink with loop 2? Very good question. Just observe here. They said it is restricted within a region of radius. It is restricted to only loop of radius smaller. It won't come outside. That means it will links with only loop 1. That's why you will get induced EMF in loop 1, not in loop 2. Got it? Next, question number 4. A coil of resistance 400 ohm resistance is given. R is equal to 400 ohm is placed in a magnetic field. If the magnetic flux linked with the coils varies with respect to time, that is phi is equal to 50 t square plus 4. The current in the coil at a t is equal to 2 seconds. They are asking current at t is equal to 2 seconds. Okay, so first of all, as flux is changing with respect to time, we have to find out induced EMF. So which is equal to E is equal to d phi by dt, right? Let me calculate that. So it's going to be minus d phi by dt. So differentiate this flux with respect to time. We are going to get minus 100 t alone, because 4 is constant. Differentiation of 4 is going to be 0 volt. At what value of time we need this? At t is equal to 2 seconds. So substitute induced EMF at t is equal to 2 seconds is minus 200 volt. So options are given only in terms of positives. Let's consider magnitude of this, which is equal to, magnitude of potential is nothing but EMF is 200 volts plus, then current I is equal to V by R, E by R. So it's going to be 200 divided by 400, which is equal to 0.5 ampere. Which option A is correct. Got it? Next. A conducting circular loop is placed in a uniform magnetic field. B is equal to fifth one. B is given, that is 0.025. With its plane perpendicular to the loop, that means theta is equal to 0. Plane perpendicular to the loop in the sense its area vector of the loop is parallel to the magnetic field. The radius of the loop is made to shrink at the constant rate of 1 millimeter per second. So very good. So radius is changing, that is dr by dt is changing with respect to time, with a value of 1 millimeter per second. Okay. Now the question they are asking is the induced EMF when radius is 2 centimeter. Okay. So magnitude of induced EMF is d phi by dt, where d phi is replaced as ba cos 0 by dt. So A is varying, that means dr by dt is varying. Magnetic field is constant, 0.05 Tesla. This one, bring that magnetic field outward, then area is replaced as pi r square. Pi also comes outside. Dr square by dt will be there. Differentiation of r square is 2 r dr by dt. So b into pi 2r dr by dt. Let me substitute all those values. Magnetic field is, I am replacing it with 25 into 10 power minus 3 pi into radius r is equal to 2 centimeter, 2 into 10 power minus 2 into dr by dt is 1 millimeter per second. I can replace it as just 1 into 10 power minus 3. 25 fours are 100 into 10 power minus 2 will get cancelled out. Now 10 power minus 3 into 10 power minus 3 is going to be 10 power minus 6. Then what's the answer I'm going to get? It is going to be pi microvolt. Pi microvolt is the answer. Got it? Which option matches? Option B is the correct answer. Got it? Okay, next. A rectangular, a square, a circular and elliptical loop, all in the xy plane, are moving out of the uniform magnetic field with a constant velocity v I cap. Okay, magnetic field is directed along the z-axis. Okay, the induced EMF during the passage of these loops out of the field region will not remain constant for. Okay, observe these diagrams. This is how we can arrange them. This cross represent magnetic field, cross represent into the board, dot represents out of the board here. So which is along z-axis, and plane is moving along x-axis. This is how plane is moving. When the plane is moving out, so observe these two. when these two are moving out along x direction. If you observe, their areas, change in areas are going to be constant. That means, observe this diagram. Imagine now the loop is at this position. Okay, so this much amount of area which is came out. Okay, let's say in t seconds, t is equal to, let's say in 1 second, this much amount of area came out. Then after 1 more second, will same amount of area comes out or a different amount of area comes out? Same amount of area will comes out. That means change in area which is coming out from the magnetic field region is equal to constant in this case. Similar to this, after t is equal to 1 second, let's say this is the amount of area which came out. So this is the area which came out. I am assuming it is a small area which is dA. In t is equal to 1 second. After 1 more second, same amount of area will come out or a different area. After a small interval of time, same amount of, after a dt time, same amount of area will come out. So here also dA by dt is going to be constant. Isn't it? Very good. Now let's check out with this circle and ellipse. So this is the way it is traveling. This is how loop is traveling along x direction. Now this is the area which came out in dt time. Okay, after some more interval of time, will I get the same amount of area or a different amount of area? Now observe this one. So this is how that loop is came out. So in dt time, this is the area. Now next dt time, this is the area came out. Is in for every dt time is change in dA, area is changing or constant? It is changing. That's the reason in this case dA by dt is variable. For ellipse also dA by dt is variable. So which option matches here? The induced EMF during the passage of these loops out of the field regions will not remain constant. For circle and ellipse, it is not going to be remains constant. That's the option. Which option matches? Option A is the correct answer. Got it? Check out once again. So try to see the video, whatever the explanation that I have given once again, so that you can understand it clearly. Let's move on to the next question. So okay, so question number 7. A conducting circular loop is placed in uniform magnetic field B is equal to 0.04 Tesla with its plane perpendicular to the magnetic field. That means theta is equal to 0 degrees. The radius of the loop starts shrinking at 2 mm. Already we solved this kind of model. dr by dt is given as 2 mm per second. The induced EMF in the loop if radius is 2 centimeter. Okay, they're asking induced EMF and our radius is equal to 2 centimeter. So at this condition they are asking induced EMF. Okay, EMF is equal to d phi by dt, where phi is ba cos 0 divided by dt. Cos 0 is 1 and then b is constant, pi is also constant, dr square by dt will be there. So it can be replaced again, it b pi into 2r dr by dt, where b is 0.04 into pi into 2 into r value is, what is r value? 2 centimeter. 2 into 10 power minus 2 into dr by dt. dr by dt value 2 into 10 power minus 3. So this is what they have given. So observe here, 2 into 2, 4, 4 into 2, 8, 8 into 4, 32. So it is 4 into 10 power minus 2. We can replace like that. It can finally, it is going to be, this is 4 into 10 power minus 2. 10 power minus 2 into 10 power minus 2 is 10 power minus 4 into 10 power minus 7. So finally it is 24 pi into 10 power minus 7 volt, sorry 32, right? 8 fours 32 in pi into 10 power minus 7, which can be replaced as 3.2. It is 34. It is 3 can be replaced as 3.4 into pi into 10 power minus 6, which is equal to microvolt. 3.4 into pi microvolt. Which option? Option D is correct. Got it? Okay, so next question. Let me read it out. As a result of charge in the magnetic flux linked to the closed loop as shown, an EMF V volt is induced in the loop. The work done in taking a capital Q coulomb once along the loop. General formula for work done or potential is equal to work done by charge, right? Then work done is equal to Q into V. Which option matches? Check out this for 8th one. Option A is the correct answer. So it's a simple question. So let's move on to the 9th one. What's the question they're asking? A rectangular coil of 20 turns and the area of cross section 25 square centimeter. Okay, number of turns are 20, area 25 centimeter square, has a resistance of R is equal to 100 ohm. Okay, resistance is also given. If magnetic field which is perpendicular to the plane of the coil changes at the rate of 1000 Tesla per second. Okay, they said magnetic field is perpendicular to the plane of the coil in the sense theta is equal to 0 degrees, and magnetic field is varying with respect to time as 1000 Tesla per second. Now question they're asking is current in the coil. First of all, let me find out induced EMF. Induced EMF is d phi by dt, which is equal to d into phi value b into a into cos 0 divided by dt. Cos 0 is 1. Area R is also given, it is 25 into, so this formula is replaced here like a into dB by dt, because magnetic field is changing with respect to time, but area is constant. Area is 25 into 10 power minus 2, sorry, square centimeter, right? Centimeter square, it is going to be 10 power minus 4 meter square. 1 centimeter is 10 power minus 2. 10 power minus 2 square will be 10 power minus 4, and dB by dt value is 1000, which is 10 power minus 3. So induced EMF is going to be 2.5 volt. I need current. So what is the number of turns here? We didn't consider here. Number of turns is multiplied with n here. N into d phi by dt. So into n multiplied with n. What's the value of n? N is equal to 20. Then E is equal to 2.5 into 20 is equal to 50 volt. Now I need current. So I is equal to E by R, right? So E value 50 divided by 100, which is equal to 0.5 ampere. Which option matches? Option C is the correct answer. Got it? Okay, let's move on to the next question. That is 10th one. So a magnetic field of 2 into 10 power minus 2 Tesla acts right angles to a coil area 100 centimeter square. For coil area, it is right angle, then with the turns 50 turns. The average EMF induced in a coil is 0.1 volt when it is removed from the field in t seconds. Then the question they're asking the value of t seconds. Okay. Formula for induced EMF is d phi by dt, which we can replace this as simply phi by t. So 5 is the given number of turns also, just replace it as n into ba divided by time. Then from this, time t is equal to NBA by induced EMF. Then t is equal to n value is 50 magnetic field development. Magnetic field is 2 into 10 power minus 2 into area is 100 into 10 power minus 4, 100 centimeter square the equivalent. So divided by value of induced EMF 0.1 volt. That's what I have to find out. Okay. 50 into 2 is 100. It will get cancelled out. 100 into 10 power minus 4 is 10 power minus 2. 10 power minus 2 by 10 power minus 1 will be 10 power minus 1 itself, which is equal to 0.1 second is the answer. So option B is the correct answer. Okay, so let's move on to the next topic, that is Lenz's law and conservation of energy. Okay, so let me read out that question. An electron moves on a straight line path xy as shown. The ABCD is a coil adjacent to the path of the electron. What will be the direction of current, if any, induced in the coil? Okay, so what is the condition for induced EMF? When there is a flux linkages, definitely EMF induces, and if the coil is closed, so there will be a current flow. Then what about Lenz's law? Let me explain you that. So according to Lenz's law, effect always opposes the cause, correct? Effect opposes cause. Okay, so let me explain you that. So generally formula for induced EMF, E is equal to minus d phi by dt, right? So when there is a flux changes, then EMF induces. If coil is closed, then what happens? Current flows. In which direction it will flows, so that it opposes changes in flux, so that it opposes changes in flux. Okay, this is the process that we have to follow. Okay, so let me answer this question. This is how a loop is. This is A, B, C, D. Okay, so and this is how electron is moving. First it is traveling from left, so this is X, Y. Let's say when electron is moving like this, direction of current is towards left, right? So direction of current is towards left. So it's like a current carrying conductor. So this loop is right side of the current direction. So according to right hand thumb rule, you can use that and you can find out direction of magnetic field here. As electron is moving from X to this position, let's say point C, what happens to flux linkages? Increases or decreases? Increases. In which direction it will increase? So first thing, tell me whether it is increases or decreases. Yes, it will increases. As electron is moving towards this, towards right, flux linkages increases. Okay, so let me write X, Y, Z. So when electron is moving from X to Z, d phi by dt increases or decreases? Increases. Then what happens to EMF? Induces. If EMF induces, current flows, because this coil is a closed coil. On direction of current is going to be opposite to the rate of change in flux linkages. That means here magnetic field is into the board, which is increasing. To get direction of current, we have to induce magnetic field opposite to its changes. Nothing but magnetic field should be out of the board. Then current direction is going to be anti-clockwise direction. Okay, next one. As electron is moving from, observe this, electron is moving from Z to Y, then d phi by dt will decreases, because electron is moving away from the loop, right? In this case also EMF induces. Why EMF is inducing? There should be, for inducing EMF, there should be changes in flux linkages. Whether it is increasing or decreasing does not matter. Whether changes of flux is occurring or not, that is more important. Now whether it is increasing or decreasing doesn't matter. EMF induces, then current flows. How this current flows? Now flux is decreasing or increasing? Decreasing. Then what should I have to do? I have to increase. To increase, I have to produce magnetic field into the board. That means current direction must be clockwise. If you observe here, as electron is passing this loop, current direction is changing twice. Now observe, the very first option itself is very clear over there. The current will reverse its direction as electron goes past the coil. Yes, it is. First option is correct. Let's move on to the next. A metal ring is held horizontally and a bar magnet is dropped through the ring with its length along the axis of the ring. Okay, so this is how the diagram is. A bar magnet is dropped. Imagine this is a north pole and this is south pole. It's just a loop metal ring. They didn't set current is flowing through this. It's a metal ring. What is the direction of magnetic field lines of a bar magnet? So they are from north to south. Outside the magnet, inside the magnet, south to north. This is how. And here the magnetic field lines will interlink like this. If you observe, as magnet is moving downward, so this flux produced by the bar magnet is linking with the coil. Yes, it is. Will it produce a EMF? Yes, it is. Now, flux of bar magnet, observe carefully, is linking with the coil. Okay, so if it is linking with the coil, that means there is a change in flux with respect to time. Will EMF induces? Yes, EMF induces. If EMF induces, will current flows through the coil? Yes, it will flows because it is a closed coil. Okay, in which direction this current will flow? So that it will opposes the changes in flux. What is the acceleration with which this bar magnet is moving downward? Generally acceleration due to gravity. Just because of the coil it will changes. How? So current is flowing in the coil, we have to decide the direction. How a current will flows? So that it will opposes the changes in flux linkages, right? In this case, flux linkages are increasing or decreasing? Increasing. Then what should I have to do? I have to decrease. To decrease flux linkages, in which direction current should flow? It should flow in anti-clockwise direction. Here it is. This is how current should flow. So this is induced current, so that which opposes the increases. So what is the direction of magnetic field produced by this current carrying loop? This is how it is. Is this opposite to magnetic field of this bar magnet? Yes, it is. Then an opposite repulsion force will act on this north pole. In which direction? Upward direction. If repulsion force is acting, then acceleration is not going to be g anymore. It is going to be less than that. So acceleration of the magnet is less than g, just because current carrying loop is producing magnetic field which is opposite to magnetic field. So it is a repulsive force. Definitely net force reduces, which reduces acceleration of that magnet also. Hope you understood. Okay, let's move on to the next. Which option is correct? Option C is the correct answer for question number 12. Got it? Next, Faraday's law is a consequence of very good. It's a consequence of energy. So direct answer. Let's move on to the next topic, that is electromotive force, motional electromotive force. Okay. Before solving numericals based on this motional EMF, I would like to give you a note. EMF, electromotive force. When a conductor is moving in a magnetic field, definitely an EMF will induces in that conductor, and the formula for induced EMF is equal to E is L bar dot V bar cross P bar. Just remember this formula. So this L bar represent displacement, where V is velocity of the conductor, and B is magnetic field. When all of them are perpendicular with each other, if L, V and P are mutually perpendicular with each other, then E is equal to BVL. Most of the cases, this is the formula we are going to deal with. Let's get started. A cycle wheel of a radius 0.5 meter, okay, R is equal to 0.5 meter, is rotated with a constant angular velocity. Omega is equal to 10 radian per second. In a region of magnetic field 0.1 Tesla, magnetic field is equal to 0.1 Tesla, okay, which is perpendicular to the plane of the wheel. The EMF generated whenever a coil is rotated with an angular velocity, we have a direct formula, that is induced EMF is equal to B omega R square by 2. We have a derivation for that. So when a coil is rotating, this formula is applicable if a coil is rotating in a magnetic field with some angular velocity. This is the formula that we can use directly. So formula on 1 by 2 into magnetic field is 0.1 into omega value 10 into radius is 0.5. So 10 0.1 will get cancelled. Answer is going to be 0.125. No, it is not. It's 0.5 square, right? Radius square, 0.5 square. 0.5 square is 0.25 divided by 2, which is equal to 0.125. This is the formula for induced EMF, 0.125 volt. Which option matches? Option B is the correct answer. Okay, so let's move on to the next question. Question number 15. So in chapter moving charges and magnetism, we came across a point, if a long straight current carrying conductor is there, then it will produce a magnetic field, and the magnitude of magnetic field at a perpendicular distance A is mu naught I by 2 pi A. Hope you remember that formula. Based on that formula only, we are going to solve this question right now. Okay, let me read it out. A conducting square of a frame of a side A and a long straight wire carrying current I are located in the same plane as shown in the figure. What is the meaning of a long straight wire? A wire of length infinity. That is the meaning of a long straight wire. Observe the diagram that they have given. So I've drawn here. Just check it out. So this is of infinite length conductor. Okay. So as this coil is right side of this current direction, so direction of magnetic field will be into the board like this. And as you are moving away from the conductor, magnetic field decreases. Just check it out. Magnetic field goes on decreases as you are moving away from it. Okay. So distance, I'm naming this as a different loops here. 1, 2, 3, 4. If you check it, loop 1 and loop 3, and these two loops only, magnitude of magnetic field is going to be different. But on loop 2 and loop 4, it's going to be same. We're not going to think about those two loops. We are going to think about only loop 1 and loop 3. Okay. First of all, let me find out magnetic field on loop 1. What is the distance of loop 1 from the current carrying conductor? So this is the distance I need, and this distance is total distance is x and this distance is a by 2. I'm going to get it is as x minus a by 2. Check it out. And this is a by 2. So distance of third loop from the current carrying conductor is x plus a by 2, whereas a distance of a first conductor is x minus a by 2. Okay, let me substitute all those values. Formula for magnetic field at a perpendicular distance due to infinite length current carrying conductor is mu naught I by, I is a capital I here, mu naught I by 2 pi into perpendicular distance, which is x minus a by 2. Already decided direction. Now what about B3? B2 and B4 are same, so equal force will act on it, so there is no change in any flux linkages, no need to consider about that. What about B3? B3 is equal to mu naught I by 2 pi into x plus a by 2. So you have to decide which is greater, which is lesser. Definitely B1 is greater than B2, right? As from the current carrying conductor, magnetic field always decreases. Then I have to find out net induced EMF. On which conductor EMF will be more? Definitely on first conductor. So E net is equal to, can I write down it is as E1 minus E3? Yes, it is. As I said earlier, when B, L, V, B, all of them are perpendicular with each other, just check out this magnetic field is into the board. Length of the conductor is assigned like this and V is towards right. All of these three things are perpendicular with each other. Then formula for what do you call EMF is simply BLV minus B1LV. So B2LV, where L is A here, that is the side of the square, and V is V itself. So let me bring out those two things out. So it's going to be A into V, B1 minus B2. So let me substitute those things. So I'm substituting it here. E net is equal to, I need, they're asking EMF is, induced EMF is proportional to only. Okay. So A into V, B1 is mu naught I by 2 pi x minus a by 2 minus mu naught I by 2 pi x plus a by 2. Here mu naught I by 2 pi is constant, which will comes outside. Mu naught I A into V by 2 pi x plus a by 2 minus x plus a by 2 divided by x square minus a square by 4. So this is out. So minus x plus x will get cancelled out. Then it is inversely proportional to x square, I guess. 15. Is it? Let me check it out. Let's expand this. So it's mu naught I A V by 2 pi. I can write down it is as 4x square minus a square, and 4 goes to numerator. I have, it's going to be 4a. So this is 4a divided by a by 2 plus a by 2 is a. 4 goes to numerator. It's going to be 4x square minus a square. 4x square can be replaced as 2x square minus a square. So this 2x square minus a square can be replaced as 2x plus a into 2x minus a, right? So induced EMF is inversely proportional to 2x plus a into 2x minus a. Which option matches? Option B is the correct answer. Got it? Okay, let's move on to the next one. So 16th question. Question is, a thin semicircular conducting ring of radius r is following its plane vertical in a horizontal magnetic field as shown in the figure. Okay. Observe the diagram they have given. The question they are asking, potential or difference developed across the ring when its speed is v. Okay. Now whenever Earlier I said one formula of induced EMF when a conductor is moving in a magnetic field, that is L bar dot V bar cross B bar, isn't it? In this case, what's the meaning of L bar? It's a displacement, right? That means I have to consider this one alone. Okay, so what's the direction of induced EMF here? By using right hand rule, Fleming's right hand rule, we are finding direction of induced EMF, right? First of all, decide the direction. Forefinger indicates direction of magnetic field, thumb indicates direction of motion of the conductor, and middle finger indicates the direction of current flowing through the conductor, isn't it? Yes or no? So let's decide the direction. This is how current will flow, right? And that is the displacement we should consider. As it is flowing like this, definitely EMF symbol must be represented like this. So this is the way of representation of EMF induced in the coil. Actually, this is the imaginary exact representation is here in the coil. This is how current flows like this. That's a way of representing. This is imaginary. Okay, well, because we have to consider displacement, right? That's the reason I'm drawing like this. Okay, so what is the displacement here? Radius is smaller and displacement is going to be 2r. So it's going to be BLV, right? As all of them are perpendicular with each other. So B into V into L is 2r. Which option matches? 2r into BV. Very good. And one more thing, which is at a higher potential? R is at higher potential because R is connected to positive, right? Check out this. Yes, it is. As R is connected to positive, that is the higher potential. Super. P is lower potential, R is higher potential. This is also called as VRP, which is equal to VR minus VP. Got it? Next, question number 17. A straight line conductor of length 0.4 meter moved with a speed of 7 meter per second perpendicular to the magnetic field. Okay. Question they're asking is induced EMF across the conductor. Okay. Formula for induced EMF is BLV. So as all of them are perpendicular with each other, B value is 0.9, L value is 0.4, V value is 7. Just multiply all these things, you'll get the answer. So if you multiply this, you are going to get an answer approximately 2.5. Not approximately, exact answer you are going to get. This is the induced EMF. Okay. Okay, so let's move on to the next topic. That is energy consideration or a quantitative study. Okay. Okay, let me read it out. A long solenoid of diameter 0.1 meter has 2 into 10 power 4 turns per meter. Okay. Question number 18. Solenoid length is equal to 0.1 meter, has number of turns per meter, that means small n they have given, which is 2 into 10 power 4. Difference between small n and capital N is simply number of turns, where small n is number of turns per unit length. Okay, so this is turns per meter. Okay, next. At the center of the solenoid, a coil of 100 turns and radius 0.01 meters placed with its axis coinciding with the solenoid. Okay, super. Let me show you the diagram. Observe this solenoid of length 0.1 meter. Now, inside this solenoid, at the center, one more coil is placed, which is of 100 turns. A coil is placed like this, which is of 100 turns. This one is of 100 turns. Okay, so that its axis is coinciding solenoid. This is the meaning. Okay, this is the axis which is coinciding both the things. Okay. What's the radius of this coil? Radius is given as R is equal to 0.01 meter. This is for this small, let's say coil 2, and this is coil 1. Solenoid also I am treating it as a coil only. Now the question. So the current in this solenoid reduces at the constant rate from 0 ampere. So to 0 ampere from 4 ampere in 0.05 seconds. Okay. So current is reduced. Current is reduced to 0 ampere from 4 ampere in 0.05 seconds. What does it means? There is a change in current. If there is a change in current, definitely there will be a change in flux also, right? If the resistance of the coil R is equal to resistance of the coil is 10 pi square ohm, the total charge flown through the coil during this time. Okay, so as current is changing in the coil, so what is the initial flux and final flux? That's what we have to find out. Okay, okay, so let me find it out. Formula for magnetic field of a solenoid at the center is mu naught Ni. So there are two different cases we have. In a first case and a second case. In a first case, current is I is equal to 4 ampere. In a second case, I is equal to 0. So in a second case, that is B2 is going to be 0, right? So B2 is equal to 0. In the first case, B1 is not equal to 0. Then what's the formula for induced EMF? Induced EMF is equal to d phi by dt. We can replace this EMF. Let me find out current. Current is equal to I is equal to 1 by R into d phi by dt, right? So, and this current is replaced with the charges d cube by dt. This dt will get cancelled out. Then you can write down Q is equal to delta phi by R. Okay, where delta phi is the total flux change and R is the radius. With the help of that, we can find out. So let's find out this. Q is equal to delta phi is phi final minus phi initial, right? So we are finding magnitude divided by R. R is radius of the coil. Which coil I have to consider? So solenoid current is flowing, which produces magnetic field. That magnetic field interlinks with the coil, which produces EMF. I am finding current charge flowing through the coil. Why charge is flowing through the coil? Due to flux linkages. Why flux is changing? Because of there is a change in current in the solenoid. So this is what you have to consider. If flux is related, change in flux we have to find out. That is, what is the formula for flux? B into A, right? So what's the formula for B? Mu naught Ni. Okay, so let's find out. So formula for what is the phi 2 value? Phi 2 is 0, no? Because B2 is 0. Phi 2 is 0. I have to find out phi I alone. So that too only magnitudes. I am writing it directly. It is B into A into number of turns n. So B is equal to mu naught Ni. Okay. So magnetic field is produced by the solenoid, right? Let's find out that divided by R. R is radius of coil. So Q is equal to, I'm very clear, just check out the things. So magnetic field mu naught is 4 pi into 10 power minus 7. Small n, number of turns per meter is 2 into 10 power 4. B is magnetic field produced by solenoid, and that is interlinking with the coil which is placed inside. In that coil, current will flows and charges also flows. So 2 into 10 power 4. Current in the solenoid is final current of 4 ampere. Okay. Into whose area I have to consider? I have to consider area of the coil. So because in the coil only I am finding charge, no? So which is equal to what is the radius they have given? Radius is 10 pi square, no? It's going to be pi into 10 into pi square whole square. Once check out this substitution. So this is we substituted wrongly. So radius is 0.05 something 0.01. Coil radius is 0.01. So let me substitute that. It is pi r square, that is 0.01 square into what is the number of turns of the coil? It is 100 divided by what's the radius? Radius is not radius, capital R is radius of the resistance of the coil, which is 10 into pi square. So this pi square will get cancelled. Then it is 10 power minus 4, 10 power minus 2 whole square, 10 power minus 4, 10 power minus 4, 10 power plus 4 will get cancelled. So here I have 100, 1 0 will get cancelled. 2 4s are 8, 8 4s are 32. What I'm left with? Okay, correct. So here I have 10. 10 into 10 power minus 7 is 10 power minus 6. So final answer is 32 into 10 power minus 6 coulombs. So it can be replaced as they're asking in terms of micro. So 32 micro coulomb. Which option matches? Option B is the correct answer. Got it? Next. Let's try next question. In a coil of resistance 10 ohm, the induced current developed by the changing magnetic flux through it is shown in the figure as a function of time. That means current is changing with respect to time. Okay. Magnitude of change in flux through the coil in Weber. Okay. We know the formula for charge in terms of flux. That is Q is equal to delta phi by R, where R is resistance of that coil, Q is charge flown, delta phi is change in flux. So here the relation, this is what. Okay, so let's use that relation. First of all, I have to find out charge. So general formula for current in terms of charge is I is equal to dq by dt. So to find out charge, I have to integrate current with respect to time. Meaning of integration is nothing but area under the graph, because they have given graph, right? So area under graph. First of all, let's find out the area of that graph so that we can equate it. So it's going to be 1 by 2 into side base is 0.1 into height is 4 into bring this resistor here, resistance is 10, which is equal to delta phi, and the answer is 2 Webers, I guess. Which option matches? Option B is the correct answer. Got it? So that's the way to answer. Next, question number 20. For question number 20, direct answer. So they're asking electric charge passes any point in the circuit in dt time represented by. So direct answer, just given a derivation now. So Q is equal to delta phi by R. So don't need to solve that. It's the direct formula based question. Okay, next. The total charge induced in a conducting loop when it is moved in a magnetic field depends on total charge. Formula 21. Formula, total charge formula, Q is equal to delta phi by R, right? Let's check out that. Total charge is the rate of change of a flux or initial magnetic flux only, or total change in flux on which it is depending upon. 21 option C is correct. Sorry. Because Q is directly proportional to delta phi by R, right? It is proportional to delta phi, that is total change in flux, and inversely proportional to resistance of the coil. If you observe here, which option matches? Option C is the correct answer. It depends on total change in flux. Got it? Okay. Hope you understand. So don't think like I'm taking I solved this question in these many steps. I'm just solving this by using these many steps just to make you understand. Okay, if you understand this, you can use you can reduce some steps so that it is very easy to solve it in very less time. Got it? Okay, let's move on to the next topic.